3, 2, 1. Time for another Math 2070 online video. And as a follow-up to a previous video, we'll now investigate some properties of determinants. So last time we introduced the idea of a determinant for a 3 by 3 and beyond. The determinant of a 2 by 2 we had already encountered, the AD minus BC, the magic number detecting invertibility for a 2 by 2. And as we'll see, you'll find out that invertibility can be detected using determinants for larger size matrices as well. But as we saw, computing determinants can be pretty computationally vexing. And as we saw, for triangular matrices, computing determinants is quite easy. So it'd be nice if I could perform some row operations, create a upper or lower triangular matrix, and then just go, well, the determinant is the product of the diagonals, so we're good to go. The problem is that all row operations don't leave the determinant alone. Some of them are going to change them. And as we're going to see throughout this experiment we're about to perform on the following matrix, we'll be able to predict what row operations will do, and furthermore, we'll see kind of why the cofactor expansion is the way it is. So we'll experiment with this matrix, 1, 2, 1, 3, 4, 0, 1, 1, 1. We see a column, or a row, that has a 0 in it, so we're going to cofactor expand on that. I'm picking the column, the cofactor expand. Note that I've got plus minus a positive 1 here. Likewise, I'll have a positive 1 down there. So I delete the row and the column for this, and what's left over is 3, 4, 1, 1. I take the determinant of that. I delete the row and the column of this. What's left over is 1, 2, 3, 4, and I compute the determinant of that. And the determinant here, 3 times 1 minus 4 times 1 is negative 1. And 1 times 4 minus 2 times 3 gives me negative 2. So this matrix has a determinant of negative 3. All right, not too bad. All right, let's start doing some row ops. So, for example, let's take negative 1 times row 1 and add that to row 2. I chose that to zero out this middle entry. And now I see a row where I could do a nice little cofactor expand. So let's do that there. But note now, plus, minus, plus, this is a minus here. And this is a minus. And when I delete the row and the column of the corresponding entries, here I'll pick up a determinant of 1, here I will pick up a determinant of negative 1, and ooh, would you just happen to know it, I got the same value. Now, note here, if I did not include my minus sign shenanigans, if I let that be a positive 1 and a negative 2, I would not have arrived at our original determinant value. Oh, interesting. Maybe cofactor expansion is built off of I want row operations to not do anything. And in order for that to happen, when we do our little deletion of rows and columns, we need to make sure a plus and a minus is showing up. Ooh, maybe. Interesting. Also, oh my god, excuse me. Conveniently, look at that. Oh my god, I'm dying. Give me a second. Conveniently, we ended up with getting the same computation as negative 1, negative 2. That was nice. Alright. Moving right along. Let's do another one of our row ops. Let's swap row 2 and row 3. Okay, and do our cofactor expand. So again, we'll do it on column 1 there. But note now, my entry has this minus sign, which, again, I've kind of alluded to. We kind of needed that for the cofactor expand to ensure that the row operations don't do anything. But as sort of a byproduct of that, here we see that now I've actually negated my determinant. So swapping row 2 and row 3 gave me my original determinant, but negative. And similarly, let's scale our final row by 3. Remember, there was a big fat row of 1s down there. And again, we do our cofactor expand, and we'll do column 3 again, because we got the 0 in the middle. And here you see that, hey, a factor of 7 appeared twice, and I was able to pull that out, and I got 7 times the original determinant. Oh, that's pretty exciting. So all three of these were not happenstance. This is what always happens. So if you scale a row and add it to another row to create a matrix B, you never change the determinant. The way cofactor expansion is built ensures that these sort of row operations like this are unchanged. So if you really want to dig deep, there's a property called n-linear or row linear, and the determinant is a particularly unique function that preserves that kind of linearity. So for the deep lore enthusiasts, go ahead and look into it. In a brief moment here, I always want to point out that this to me is like the most blurst result in mathematics, because it really feels like scaling a row and adding it to another should absolutely annihilate your determinant. It should, right? Scaling a row and adding it to another like fundamentally alters like the structure of your matrix. Swapping two rows moves things around, but like it's still the same matrix, just moved around. And scaling a row also just sort of takes what you have and just mildly modifies. Scaling and adding a row like introduces zeros. It really feels like this is the one that should do something, but it does nothing. And again, there's some deep reasons for that. Like I mentioned, there's a thing called n-linear or row linear that I'm kind of sweeping under the carpet. And according to a very snarky reply I got on Reddit once, obviously this one is true. Because the determinant corresponds to the volume of a parallel pipe head, and a row being scaled and added to another is a shear transformation of the plane, and by Cavaleri's principle, we know that a shear transformation of a volume is going to remain preserved under its operation, so clearly this is true. Anyway, so moving on. So swapping two rows, negating it, we kind of saw that in action what that did. It sort of moved things in certain spots that, by the cofactor expansion, introduced a minus sign in the right spot, and then moving the rows around in the 2x2, then sort of flipped the switch and made those negative as well. And that always happens. You interchange any two rows, you negate the matrix. And finally, if you scale a row by a non-zero scalar, then clearly the determinant gets scaled accordingly. And that's like really obvious to see because the scalar appears either in the entries that you're multiplying by, or in the rows that are appearing in the minors. So that one's not too shocking to see that that's true, and as a neat little consequence of that, that reveals to us that determinants aren't a linear operation, but if you scale a matrix, you can predict what it's going to do, because if you scale a matrix, you scale every row, so there's going to be n factors of alpha showing up. Pretty neat. Now, as a consequence to all of this, we find that I can perform row operations, and as long as I'm keeping track of things, I can compute the determinant. So if I wanted to row reduce my matrix to a upper or lower triangular matrix, and then take the product of the diagonal entries, I can totally do that, and that'll work. But I do need to be mindful about what row operations I performed and how those affect the determinant. Now remember, any matrix is invertible precisely if it's row equivalent to the identity matrix. The identity matrix, we note, has a non-zero determinant. And by all of the facts we just stated, row operations will never make the determinant zero unless it was zero to begin with. Right? If we look at these three, this doesn't change the value of the determinant. This negates it. So the only way I got a zero for the determinant of B is if the determinant of A was zero. And likewise, scaling by a non-zero thing, well, the only way the determinant of B was zero is if the determinant of A was zero. So no row operation can make the determinant zero unless it was already zero to begin with. And as noted, the identity matrix is a non-zero determinant, so you are invertible precisely if your determinant is non-zero. There we go. As promised, the magic number detects invertibility. Now, another neat little consequence of this, and this is one of my most favorite consequences in mathematics, any randomly selected n by n matrix is almost surely going to be invertible. And that's because the determinant is 0 when you're not invertible. If you were to randomly pick a real number, what are the odds you picked 0? Very right. Just randomly grab something off of the number line. You most likely didn't hit 0 because it's a single point. So any randomly generated n by n matrix is almost surely going to be invertible. And what's really nice about this is for real-world applications, pretty much any n by n matrix you collect, like if you're doing some data and you just collect a bunch of data and you have like a 4,000 by 4,000 matrix, it's almost completely guaranteed it's going to be invertible because there's going to be noise, miscalculations or whatever. What you're going to have is not essentially random, but there's basically no hope that it's actually not invertible, because then you need the determinant to be 0, which is such a specific thing, there's just no way it can happen. And if you don't believe me, I wrote a... oh man, this didn't look that blurry before. Anyway, I wrote a little Python script to randomly generate a million 3x3 matrices and then compute the determinants, and then kept track of all the ones with non-zero determinant, and guess what? All of them had non-zero determinant. So, it'd be interesting if how big I need to make this to finally have it randomly create one that wasn't invertible. I don't know, or the odds of it ever actually showing up. Right? It's like it's probability 0. Now again, probability 0 doesn't mean that it will never happen. It just means that the odds of it happening are so minuscule that it's Like a good example of that is if you're sitting in a room, it is entirely possible all of the air molecules will fly into the corner of the room and you'll suffocate. Right, but what are the odds of that actually happening? All right, let's wrap things up with 2 more properties of determinants, and let's experiment, this time on 2x2s. Let's not go crazy. And let's just play around with these 2x2 matrices. These have pretty easily computed determinants. They're both easily seen to be negative, too. And note that matrix A, when I take its transpose, A, the determinant didn't change. And likewise, when I take the product of A and B, the product of the determinants gives me the determinant of the product. Hey, our favorite phrase in mathematics, the x of the y is the y of the x. And in fact, this is always true. Now, the transpose is really easy to justify because transposing, again, remember, swaps my rows and swaps my columns. Well, as we already noted, cofactor expansion doesn't care if you do it across a row or do it across a column, you'll always get the same value. So if I transpose, yeah, nothing's going to happen. Now, the product of the determinant being the determinant of the products, this one's a lot trickier to actually prove if you wanted to actually work out the details. But basically, it boils down to, well, if you're not invertible, then A times B can't be invertible. Well, so then the product of the determinants ends up equaling 0, so everything's good. But if you are invertible, then you're row equivalent to an to the identity matrix, which means there are these elementary matrices that you have to equal in a product, and it just so happens that elementary matrices, determinants, and products clean up very nicely and very easily. So there's a longer explanation to why the product rule works for determinants, but we'll just take it for fact, and we'll use this. And to quote, as of this recording, the chair of the math department, Professor Eric Weber, the determinant of a product being the product of determinants is like the most important thing. That is a direct quote. He said that to me once in my office. We were talking about linear algebra, like normal human beings do. And he just offhand mentioned, like, that's like the most important thing. So, if you don't want to take my word for it, you take the boss's word for it. It's the most important thing. All right, and with that finishes our brief little rundown of the basic properties of determinants. In our next video, we will look at a neat little application that relies on the most important thing ever, so stay tuned for that.